Good morning, everyone. In today's session, we are about to discuss the radiation from oscillating dipole. You can call the oscillating dipole, otherwise the Hertzian dipole or short dipole. So first, we can see what is the definition of a Hertzian dipole. So we can define Hertzian dipole as a dipole which has a length very small when compared to that of the wavelength of the signal, which is radiated. Okay, and you can say that for Hertzian dipole, the current distribution is uniform. Again, to see in detail, first we have to know what is a Hertzian dipole. So we can say that the Hertzian dipole, it consists of two equal and opposite charges, and they are separated by some distance. See this diagram. So the first diagram, it refers to a short dipole. You can see this is a dipole structure, and it is fed by means of using a balanced transmission line. And the second diagram, it refers to the equivalent circuit for the short dipole, in which two charges which are equal and opposite, they are separated by some distance L, and the current flowing is mentioned as I. Similarly, the third one, it refers to the Hertzian dipole. Here also you can see that the two charges which are equal and opposite, they are separated by each other by some distance dl, because you can say that dl is infinitesimally small length. Now we are going to analyze how the radiation will be from the Hertzian dipole. So in order to analyze, we are going to work out with the spherical coordinate system. So you know what are the spherical coordinates? R, theta and phi. Okay. So see here, as per this diagram, a Hertzian dipole which is of infinitesimally smaller length and which is represented as I naught dl, which is placed at the origin, and we are going to analyze this Hertzian dipole from some further distance p. So here p of x y z is mentioned here. So we are going to analyze from the farther distance p. So first we have to know how this works. So initially the Hertzian dipole is neutral in condition, and once the current flows in a particular direction, you can say that an excess of charge gets accumulated at one end because the current flow is unidirectional. Similarly, when you change the direction, you can say the other end the charge gets accumulated. So because of this, there will be a voltage difference between the two halves of the dipole. So since there is an imbalance between the charges in the Hertzian dipole, an oscillating current will result in oscillating voltage. And you can say if the current oscillation is sinusoidal, then the voltage oscillation will be also sinusoidal. Now to analyze, we are going to consider the vector potential, because only using the vector potential we are going to analyze the Hertzian dipole in the spherical coordinate system. So the vector potential is denoted as A. So A, it is a function of r theta and phi equal to mu by 4 pi over the integral I of x dash, y dash and z dash into the exponential term e power minus jk r by r into dl dash. So since we have the infinitesimal current element at the origin, you can say that x dash, y dash and z dash all are equal to 0. So now we can apply the equation between the 2 points. One is the origin and the other the point P where we are going to measure, where we are going to analyze. So that is r equal to root of x minus x dash the whole square plus y minus y dash the whole square plus z minus z dash the whole square. So since x dash, y dash and z dash are 0, we can take r is equal to root of x square plus y square plus z square. And again we are considering this is equal to r, small r. Now we have considered the infinitesimal current element, that is I is equal to I naught into dl actually. And since this is directed along the z direction, so we are representing by the unit vector az. Okay. So now we can replace the vector potential by means of substituting the current I is equal to y naught az dl. So the equation will be in this manner. A of r theta pi is equal to az mu by 4 pi I naught dl e power minus jkr by r. And we are considering this term, that is mu by 4 pi I naught dl e power minus jkr by r. We are taking it as az, right? Now we are analyzing using the spherical coordinate system, and so the components r theta and pi has to be related with that of the vector potential az. So this is the equation. You can see here ar equal to az cos theta, a theta equal to minus az sin theta, and a pi equal to 0. Now we'll take the curl function for the vector potential A. So del cross A is equal to, you can see the matrix 1 by r square sin theta, AR or A theta, r sin theta A pi, dou by dou r, dou by dou theta, dou by dou pi, AR or A theta, then r sin theta A pi. So now we have to expand the matrix. So before going to expand, we need to substitute, because already we have seen, we have found AR, A theta and A pi. We have the relation. So those equations has to be substituted in this matrix. So the equation gets modified, the matrix gets modified as in equation number 2. Now we can say that the function az, it is with respect to r, so the derivative terms with respect to theta and pi becomes 0. Now when you expand the matrix, you can see the matrix is expanded. uh, See the terms, the required terms gets cancelled, and the reduced equation is equation number 3. Del cross A is equal to 1 by r A pi dou by dou r of minus r az sin theta minus dou by dou theta into az cos theta. Now in this equation we have the term az. So already we know what is az, so that particular equation has to be substituted. And after, so for the simplification, we will be arriving at the equation, that is del cross A equal to 1 by r A pi az sin theta into jkr plus 1. So all substitutions are made and we are simplifying the equation, and finally we are arriving at the equation number 4. So del cross A is equal to 1 by r A pi az sin theta into jkr plus 1. Now again we have to find the magnetic field component. So in order to find the magnetic field components for the Hertzian dipole, we are going to apply the curl function with respect to the magnetic field H. So the relation is H is equal to 1 by mu del cross A. Now as per the vector theorem, we can expand H. So H is HR AR plus H theta A theta plus H pi A pi. That is equal to 1 by mu into del cross A. Now we have the only component h pi, because the previous equation, that is a pi az is a function of a pi, so we have the terms hr and h theta as 0. So h pi a pi is equal to 1 by mu del cross A. Already we have found del cross A as in equation number 4, so that equation is now substituted, and after simplification we arrive at the equation number 6, h pi equal to 1 by mu 1 by r Az sine theta into jkr plus 1. Okay, so in this equation number 6, we need to substitute the value for Az as we have done earlier for the electric field components. So after substitution of Az, the equation gets simplified as equation number 7. Now we are doing further simplification. After cancellations of the required terms, the equation h pi reduces in this manner as equation number 8, jk I naught dl sine theta by 4 pi e power minus jk r by r into 1 plus 1 by jk r. Okay. Now we are analyzing the Hertzian dipole. That means we have to see what will be the electric and magnetic field components. So we have to derive all the components, required components, both for the electric as well as the magnetic field. Now, in order to find the electric field, we are going to apply the Maxwell's curl equation. So del cross H is equal to J plus J omega epsilon E. So for source-free region, the conductivity J is equal to 0. So the equation reduces to del cross H equal to J omega epsilon E. Now from this equation you can find E. So E is equal to 1 by J omega epsilon del cross H. Now we can find what is del cross H. Similar to the previous manner, we have to expand the matrix, and already you know that the components HR and H theta are 0, and the only component available is H pi. So we need to substitute the value of H pi. So we are in the equation number 10, you can see that the terms HR and H theta is equal to 0 is substituted, and in the equation number 10 we are further going to substitute the value of H pi. So the equation is now modified. So we have the electric field equation 1 by j omega epsilon into 1 by r square sine theta and the terms within the matrix. So we are expanding this matrix now, and the expanded form of the equation for E is the equation number 11. Now we can expand E, that is E is equal to ERAR plus E theta A theta plus E pi A pi. This is equation number 12, and from the equation number 11 you can see that there are two unit vectors, one is AR and the other is A theta. So you can separate the terms, you can separate the functions with respect to AR and A theta. So the equation number 12 is equated or compared with equation number 11, and we are first finding the ER component, that is the electric field component along the radial direction. So we get 1 by j omega epsilon into 1 by r square sine theta rho by rho theta of r sine theta h pi. So now h pi is already calculated, so we can substitute that value and find ER. Similarly, when you are equating the equations 11 and 12, we are comparing the equations 11 and 12 with respect to theta. And so this is the equation number 14 refers to the E theta component 1 by minus 1 by j omega epsilon into 1 by r square sine theta into r of dou by dou r of r sine theta h pi. So now we can substitute the value of h pi in equation number 14, and after simplification the equation reduces in this manner. Er is equal to k by omega epsilon cos theta I naught dl by 2 pi r e power minus jk r by r into 1 plus 1 by jk r. Now you know k, which is denoted as k is equal to omega into root of mu epsilon. So in this equation we have the term k by omega epsilon. So we are modifying the equation k by omega epsilon, and the equation reduces to like this, is equal to root of mu by epsilon, which is eta. So this value k is now k by omega epsilon is now eta, and this value is substituted in the ER equation. So the equation reduces like this: ER equal to eta cos theta I naught dl by 2 pi r e power minus jkr by r into 1 plus 1 by jkr. So we have found the electric field component along the radial direction. Next, we can find what is the electric field component along the theta direction. As usual, we need to substitute the value of h pi, and the equation reduces in this manner. You can refer to this equation: E theta is equal to j eta k I naught dl sin theta by 4 pi into e power minus jkr by r into 1 plus 1 by jkr minus 1 by kr the whole square. So now we have found the components h pi, followed by that the electric field components er and e theta. Got it? Now we are going to see we are going to calculate what will be the radiation resistance of the oscillating dipole, which is otherwise called as the Hutchinson dipole or short dipole. And as I already discussed you, a short dipole is one in which the field is in oscillation because of the oscillating voltage and current. See, refer to this diagram. So this diagram shows the current distribution of short dipole. Can see that it is somewhat triangular in shape. The reason is we are feeding the Hutchinson dipole at the center. So since there is maximum current flow, you can see at the center there will be maximum current flow, and gradually it reduces to zero towards the ends of the dipole. So you can say the current amplitude the Hutchinson dipole is maximum at the center, and it decreases to zero gradually at the end. Now we are going to calculate what will be the radiation resistance of short dipole. So to calculate the radiation resistance, we are using the average Poynting vector formula. The average is equal to W by S, where W is the power radiated and S refers to the area. Now we can calculate what will be the total power radiated by means of taking the surface integral over the Poynting vector over the surface enclosing the antenna. So you can write W is equal to the integration of the average Poynting vector into ds. You have one more formula. The average Poynting vector is equal to 1 by 2 into real part of E cross H conjugate. So already we have calculated only one component present for magnetic field H pi, and we have two components E theta and ER for the electric field components, right? So the field components are now E theta and H pi, and we are considering the radial component of the Poynting vector as power average is equal to, or P average is equal to PR. Now instead of P average we can substitute PR, so which is equal to 1 by 2 real part of E theta cross H pi conjugate. We'll consider this as the equation number 1. Now already we have calculated the E theta and H pi components for the Hutchinson dipole, which are referred to as equation number 2 and 3. And again, you know the intrinsic impedance of the medium eta naught is equal to root of mu naught by epsilon naught, so which is again equal to 120 pi, or which is the ratio of the electric field component in the theta direction to the magnetic field component in the pi direction. So eta naught is equal to E theta by H pi. So from this we can find E theta by just cross multiplying eta naught and H pi. So we can now replace the average Poynting vector, which is again equal to the Poynting vector in the radial direction PR, is 1 by 2 real part of H pi square into eta naught. Now we can substitute the real part of H pi. So the equation becomes PR is equal to eta naught by 2 into k I naught dl sin theta by 4 pi r the whole square. So we have found what is PR. Now we can find what will be the total power of the short dipole by taking the double integral of the pointing vector in the radial direction. So W is equal to double integral over PR into ds. So already we have calculated PR. So the equation reduces in this manner. You can see we have double integral. One is over the limit 0 to 2 pi and the other 0 to pi. Now W is equal to eta naught k square I naught square dl square by 2 into 16 pi square. First we are integrating with respect to d pi. So integral over the limit is from 0 to 2 pi d pi, and we have to integrate the value of sine cube theta d theta. So the limit is 0 to pi. So first we can find what is the value of the integral 0 to pi sine cube theta d theta. So we have to apply the sine cube theta formula, and after further simplification we finally get 0 to 2 pi sine cube theta d theta is equal to 4 by 3. So the equation get reduces to W equal to eta naught k square I naught square dl square by 16 pi into 4 by 3. So we have substituted the value of the integration of 0 to pi sine cube theta d theta. So after simplification, finally the equation reduces. W is equal to root of mu naught by epsilon naught k square I naught square dl square by 12 pi. So this is the total power which is radiated by the Hertzian dipole. Okay, so you can say it must be equal to the power delivered to the dipole, assuming that there are no losses, zero loss. So total power is equal to W one. We can say we are representing in terms of the radiation resistance. W is equal to 1 by 2 I naught square into R. So the radiation resistance RR is equal to 2W by I naught square. So we need to calculate what is the value of the radiation resistance for short dipole or Hertzian dipole. So already we know the value for W, the equation for W. So that equation is substituted here, and finally we are getting RR is equal to 20 k square to L square. So k is 2 pi by lambda. From this simplification you can know k is equal to 2 pi by lambda. So the equation reduces to RR is equal to 80 pi square into L by lambda the whole square. Now we can substitute the value of pi, which is 3.14, and after substitution we get RR is equal to the radiation resistance is equal to 789.57 into L by lambda the whole square. So this gives the radiation resistance of the short dipole. Next, we are going to calculate what will be the effective aperture and directivity of short dipole. As you know, the formula for the maximum effective aperture is V squared by 4S into the radiation resistance RR. Now, here V refers to the induced voltage. We can represent V is equal to E into L, and S refers to the pointing vector. So S can be represented as S is equal to E into H. And just now we calculated what is the radiation resistance, which is 80 pi square into L by lambda the whole square. So after all values are being substituted, we finally get the maximum effective aperture for the Hertzian dipole is 0.1193 lambda square. Now you know the formula for directivity. So directivity D is equal to 4 pi by lambda square into the maximum effective aperture. So the value of the maximum effective aperture is substituted, which is 0.1193 into lambda square. And after simplification, we can finally conclude that the directivity of the short dipole, otherwise called as the short dipole, or the Hertzian dipole, which is equal to 1.5. So in the very next session, we can discuss about the half-wave dipole and what will be the radiation mechanism for the half-wave dipole. Similar to the previous case, we have to derive what are the electric field and the magnetic field components for half-wave dipole. Thank you.